All right, let's do this. So happy holidays to you all. Perfect apropos topic here. Chemical kinetics is very scary stuff, so perfect for the holiday. All right. Actually, it's not too bad here. So first of all, we spent last chapter talking about thermodynamics, which was very much so whether or not a reaction occurs spontaneously in the forward direction towards the products or in the reverse direction towards the reactants, right? So always measuring, which direction is a reaction actually going to go. Kinetics is a very different topic that seems like it would be very closely related, but is actually completely different. And this corresponds to the speed of reactions. How quickly are reactants being converted into products? All right, and again, that's very tempting to think that these are one and the same thing, that a reaction that's spontaneous will be really fast, or a reaction that's non-spontaneous will be really slow. Turns out that they are completely separate topics. The world is full of very, very, very favorable reactions that occur at just ridiculously slow rates, okay? One classic example, you would have learned in your biology classes that in biology, ATP is used as like the energy currency in the cell, right? So what does that mean? That means that breaking that phosphodiester bond, whatever fancy name, bond in ATP releases a ton of energy. It's a very spontaneous reaction, very large negative delta G associated with that reaction. So your body pairs that very favorable reaction with very unfavorable reactions, like building proteins, creating a lot of order, okay? So then why aren't we just worried about all the ATP in our body just spontaneously falling apart and releasing a ton of energy? Well, it will, spontaneously, but at a scale of tens of thousands of years. We'll be long gone by then, right? So this reaction, despite being very, very favorable, occurs really, really slowly. Your body ends up using enzymes to catalyze it to make it happen on a quicker time scale, okay? Bottom line is whether or not a reaction occurs favorably, whether or not it's spontaneous is completely different than whether or not it occurs quickly. So we study these topics very separate from one another. And again, today we're introducing this chapter on kinetics. So this is now the study of reaction rates, speed of reactions. All right? So first thing I want to do is I want to introduce you to this diagram here that kind of sums up a lot of those what we did last chapter and what we're going to do this chapter. Okay? So we have this random reaction here. Hydrogen gas being combined with oxygen gas to produce water. All right? And this is what we call a free energy diagram. Okay, so on the y-axis we have free energy, and on the x-axis we have reaction progress. Okay? So both the thermodynamics and the kinetics are illustrated in this diagram here. All right, the thermodynamics, whether or not a reaction will occur spontaneously. Remember that we said that these variables, the delta G, the delta S, the delta H, these are what were called state functions. It didn't matter the path that a reaction took. All that mattered is where you started and where you finished. That's how we were calculating delta G's for these reactions. All we were looking at was what our reactants were and what our products were, right? So the thermodynamics of this reaction are illustrated just by looking at this part of my graph here, my energy of my reactants, and the very end part over here, the energy of my products. And the difference between these two, all right, so this gap right here, this is the difference in free energy between my reactants and my products, otherwise known as delta G. Right? So the thermodynamics of this reaction are illustrated just by looking at those two endpoints. What's the energy of your reactant? What's the energy of your product? That's all we have to care about when we're paying attention to whether or not a reaction is spontaneous or non-spontaneous. And let's just note that when product energy is less than reactant, this would correspond to a delta G less than 0. So what's being illustrated in this diagram here, where the products sit at a lower energy level than the reactants, is a spontaneous reaction. All right? But then we have this hump in the middle. What happens to our free energy in the middle as we're converting reactants to products? So now this is the path that this reaction is taking here. So this portion of our graph here corresponds to the kinetics of the reaction. How quickly or how slowly a reaction proceeds. That little hump there corresponds to the kinetics of the reaction. This is what we call activation energy. The size of this hump right here is what we call activation energy. And a reaction has to overcome that energy barrier in order to get to the products. All right, so kind of how we think about this, what I think about when I have this, look at a diagram like this, is I imagine that there's a little marble over here on my reactant side. Here's my reaction. And in order to get to the product side over here, it's got to overcome this energy barrier. Okay? The bigger that energy barrier is, the slower this reaction will be. If it's a really tiny hump, it's going to hop over it, no problem. If it's a big, large hump, it's going to have a hard time getting over. All right? So what we'll see towards the end of this chapter, we won't really get to it here today, but there is a quantitative relationship between this activation energy barrier and the rate of a reaction. Okay? So again, both the thermodynamics and the kinetics are illustrated on this diagram here. Just the difference between where you're starting and where you're ending. That's your free energy, that's your thermodynamics. But the hump in the middle is the kinetics of the reaction, how quick or how slow that reaction is occurring. All right, so let's take a look at a reaction here. Whoops. So this is just kind of a random reaction we're going to use to illustrate this. All right. If I'm starting out in my flask with just these reactants here, and I have a very favorable spontaneous reaction, what's going to happen to the concentration of those reactants? Is it going to go up or down? What do reactants get, consumed or produced? Yeah, so reactants are consumed. And what about my products? What do they do? Yeah, they get consumed or produced? They get produced. So my products are produced. And importantly, the rate at which reactants are consumed and the rate at which products are produced, they have to be equal. Right? I can't have more reactant reacting than I have product being formed. Right? So bottom line is we could watch the concentration of any one of these species in this reaction. I could watch the concentration of hydrogen gas. I could get my rate that way. I could watch the concentration of my iodine decreasing. I could get my rate that way. Or I could watch the concentration of my hydrogen iodide being formed, and I could get my rate that way. They would all give me the same value, right? The rates at which reactants are consumed has to be equal to the rate at which products are produced. Okay? And importantly, reaction rates are always positive. All right, so we're going to start talking about the rates of these reactions. Whenever we report reaction rates, we always report positive numbers. All right, so I'm going to take my hydrogen and my iodine, I'm going to mix it together in this flask, and I'm going to monitor the concentration of these species over time. All right, so we do this reaction, and we get a graph that looks something like this. Okay, my red line here corresponds to the concentration of my hydrogen iodide that's increasing over time. I'm going to watch my reactant, my hydrogen gas being consumed, and what I'm going to see is that decreases over time. All right, so I start out with a bunch of hydrogen in my flask and some iodine. I don't have any product, and I'm watching these concentrations change over time. All right, that's our experiment that we're doing. Cool. So, first of all, let's just note that if we kind of followed this red curve out, you see it starts really steep at the beginning here, but as the reaction progresses and progresses and progresses, it kind of flattens out and eventually will completely plateau. What do we call the region over here where it's completely plateaued and my concentrations are no longer changing? Equilibrium, right? So this reaction will proceed until it reaches equilibrium. Okay, cool. The other thing let's note here is I'm starting out with 1 molar hydrogen gas, but this red line over here is now approaching 2 molar for my product. Why would that be? Why am I getting twice as much product as I had reactant? Let's just look at our balanced chemical equation. For every 1 mole of hydrogen gas that's consumed, I'm going to get 2 moles of the hydrogen iodide produced. I could also watch my iodine concentration. I don't have that on here. We could have a third curve on here. But again, no matter what, either one of these would give me the same value. All right? So again, rate of a reaction is a change in concentration over a change in time. That's a reaction rate. That's what we're going to be measuring here, how our concentration changes over time. All right, we would report that our units would be molar, because of concentration, per second, because again, over a change in time. All right, so I could measure the rate of this reaction by measuring the change in the concentration of hydrogen gas over the change in time. But again, reaction rates are always reported as positive numbers. And what's going to happen to the change in my concentration of my reactant? It's going to go down. I'm going to have a negative delta concentration of H here. So if we're going to be looking at our reactant, we have to multiply this value by -1. So we get a positive value here. All right, so when we're looking at a reaction rate of a reactant, we got to multiply it by -1 to keep that value positive. Or I could just monitor my rate of my product that's being produced. All right, so I would get that same rate if I monitored the change in HI over the change in time. Okay, but again, I got to get a same value when regardless of what I'm monitoring here. So I'm going to have to account for that stoichiometric coefficient of 2. I'm going to divide that concentration by that stoichiometric coefficient so that I get the same rate regardless of what I'm looking at, right? These must be equal to one another. That's a weird vertical equal sign. Okay. Using this method, we could go through for each point on this graph and measure the rate of this reaction. This is what we would call the average rate. Or we could use our fancy computer technology and some algebra, some calculus. Get what we call the instantaneous rate. Again, the change in concentration, over the change in time. But in fancy algebra speak, we use that derivative notation. All right, we're not going to do any algebra here, but importantly then, in either one of these, what does the rate correspond to on this graph? It's the slope of this curve, right? The slope of my curve corresponds to the rate of my reaction, the change in concentration over the change in time. Rise over run, right? That's what we're measuring when we're talking about a reaction rate. And we can see that for this particular reaction, and this is very typical for reactions, our rate does indeed change throughout the course of this reaction. If we look at the slope of this red curve, this reaction starts out really quick, and then as it approaches equilibrium, it gets slower and slower and slower, right? The slope of this curve starts out at its steepest and then slows down as it approaches equilibrium. Okay? So again, if I wanted to measure the rate of this reaction, I would just take my data set, right? Plot it, and I could just measure for each point the slope of the tangent to that curve, right? Rise over run. All right, that's what we're after when we're talking about our reactions, our reaction rates, how quickly our concentration is changing as a function of time. And I lost my page, hold on. All right, so before we move on, let's just put down a new chemical equation, all right? We're going to say nitrogen gas and hydrogen gas combines to give you ammonia. If we balance this chemical equation, I have to put a 2 out here to balance my nitrogens, and then a 3 out here to balance my hydrogens. So I want you to give me the rate of this reaction as a function of the concentration of nitrogen gas here. How would we calculate the rate if we were measuring nitrogen gas? All right, rates are change in concentration over change in time. But since nitrogen is a reactant, what do I got to do to this ratio? -1. Excellent. All right, so now give it to me in terms of hydrogen gas concentration. So now I have a change in hydrogen gas concentration over a change in time. Again, this is a reactant, so I'm going to multiply it by -1. But I also have to divide by that stoichiometric coefficient, by that 3 in my balanced chemical equation. All right, so if I did it the one way and I measured it with nitrogen concentration, or I did it the other way and I measured it with hydrogen concentration, again, the whole shtick is that these have to be equal to one another. Both of these would give me the same rate of that reaction. Doesn't matter what we're watching. All right, so then lastly, just finish this off. Let's do it in terms of our product, the ammonia. right, so again, change in concentration over change in time. Am I going to multiply by -1? No, because it's not a reactant, but I do still have to divide it by that stoichiometric coefficient of 2. Okay, so I can get the rate of my reaction monitoring any one of these components in my balanced chemical equation. And I think this graph looks kind of intimidating, but this would be a relatively elementary experiment for a chemist to do. I mean, we've had the ability to do this crap for hundreds of years now, right? Just monitoring how the concentration of something is changing over time. Not too bad to do. You go into your graph, the difference between the time points, the difference between, again, rise over run, you get your slope for each one of those points on that graph. So getting the rate of a reaction isn't something terribly crazy, something we've been able to do for quite a while now. So scientists have done that for a long time. They've studied a bunch of different reactions, and they tend to see the same sorts of patterns when it comes to reaction rates. All right, and these are what we call rate laws. Okay, so again, after studying bunches of reactions, they see the same common pattern over and over again, where the rate of the reaction is equal to some constant K, what we call the rate constant, and this is unique for each reaction, times the actually, let me just say before we move on here, we're going to talk about a very simple reaction where we have some reactant A being converted to product. All right, so what we would call a unimolecular, or I guess that's not quite true, a single reactant reaction here. Okay, so anyways, the rate of these reactions is equal to some rate constant K times the concentration of that reactant raised to some power n, which we call the order of the reaction. All right, and out of all the billions of reactions that they've studied, 99.9% fall into one of 3 bins, where n is equal to either 0, 1, or 2. All right, so the rate of reactions are proportional to the concentration of reactant times some constant, which is unique to every reaction, but we can calculate it, we can tabulate it in books. All right, but then raised to some power, which we call the order of the reaction. All right, so first of all, before we go on, let's take a look back at this graph here. And looking at that equation, why does it make sense that my reaction rate is decreasing over time? Again, we start out with this very steep curve right here, but as it approaches equilibrium, it slows and slows and slows. We get a shallower and shallower curve. If we look at our equation here, can anybody see why? What's happening to the concentration of reactant over time? It's decreasing, and that rate is proportional to that concentration. So as that reactant's getting consumed, according to this equation here, this number keeps going down and down and down, then yeah, the rate of our reaction is also going to decrease over time.